Good afternoon. This is CIVE 638, Sedimentation Engineering, and this is the 081 class. It's the 8th week, the first class of 2 classes that we teach every week. And the subject today is more on morphology, channel morphology. Lane relation revisited with online calculation.
Yes, we can.
Okay, cool. Well, we already reviewed the lane relation. And as you know, the way we did it is we took the lane formulation, which was a proportionality, and we basically discovered through working with these equations for a long time, years, that we could make it or we could convert it into an equation. So the difference is that and this paper is kind of a regurgitation. It's actually the same paper, but it has something added at the end, and that's where I'm going to concentrate tonight. So we have the article revisits the lane relation. Let me add the size in here, which is Lane's original relation, 1955. And we are going to come up with an equation, and it is going to be an equation of sediment transport. It's going to be a sediment transport function. In other words, to calculate sediment transport. And I've already shown to you how did I derive that equation. So I'm not going to reiterate over this because later on I'm going to show you a video and we're still going to reiterate. It's very important. So this is what we did. We first defined a sediment equation, rather a friction function, which is the one that I've used since my early days at Colorado State. The sediment transport function, which is a very simple sediment transport function, which we ascribed to Colby because he was the first one that kind of did this work back in the year 1964. And then we had to come up with some sort of diameter relation. And Strickler was very convenient and very good, by the way. Mr. Strickler, working out of Germany, exactly when, I do not remember. But Strickler is mentioned in CIVE, 1959. So it must be much earlier than 1959. And by the way, the Strickler relation is a very well-known concept. And it was in CIVE anyway, 1959. Then we put it together, we figured out the coefficients. I did stress last time we covered this, that this is algebra. So as long as we understand the mechanics, the friction, the sediment transfer, and the Strickler relation, what Strickler did is he tied basically the size to the friction, but he used Manning for whatever reason. It's interesting that he used Manning. A side story is that the Germans, in Germany, as I understand it, I have not practiced sedimentation engineering in Germany, but as I understand it from what I read, that the Germans invert the Manning equation, like the Manning is in the denominator, they put it in the numerator, and they call it the Strickler formula. And some people that kind of work in both areas have actually decided to refer to it as the Manning-Strickler or Strickler-Manning. So if you hear out there in your practice, the Strickler-Manning is just a Manning formula that has been reversed or taken the reciprocal. It's the same concept. How did Strickler get involved in this? I don't know. I'm not even going to guess. But the point is that the formula is there, and it is a very well-known formula. It's formula number 24 that I'm showing in there. The coefficient of the Strickler formula. With the Strickler formula is the relationship of Manning's in with the diameter. Okay, the sediment concentration, we already know that. The modified lane relation, applications, I already covered that ground with you in the last class. The idea is to qualitatively now, since we have an equation, we can qualitatively determine the variability or the variation of the variables. Discharge, diameter, grain diameter, hydraulic radius, water discharge, and slope. those enter into the function. I have an example in here of sediment deposition at the tail of a reservoir. This is a very large reservoir in northern Peru. And I was there. We had a project in the year 2008, 2009. Actually, it was 2007 to 2009. I had a project out there, and I visited this large reservoir, and I was able to take this picture. So what is this picture? What does it show? It's at the tail of the reservoir. It just shows the sedimentation, but through the sediment, through the deposited sediment, like I said, at the tail of the reservoir, which sediment tends to stop or settle at that point because it hits the reservoir and it all of a sudden loses its speed and then it deposits. But on top of that, we have to realize that there's got to be a flow through the deposit for flood conditions. So that's the channel in there. So what you're seeing here is just precisely the tail of the reservoir and the river going through, the river coming over here, and the main part of the reservoir is over here and towards the left. And I have another example in here, which I have already discussed with you. This picture was taken in Tijuana back in the year 1994. I was lucky that in the year 1993, they had a very big problem in Tijuana, which I'm going to discuss later on, and I'm even going to show you a video. Then in the year 1994, I had a student of mine, San Diego State, that was from Tijuana. And he invited me to go to a presentation out there to present. They wanted to learn something about hydrology, 1994. So he invited me to go out there. Like I said, he was a student of mine. And I went over there and it was a very good meeting and I met a lot of people, particularly this gentleman with whom I have worked since then for 1994. How many years is that? 28 years. I worked with that gentleman for 28 years. As a matter of fact, I have him in my video of the site. So what happened here was that there was an instance which must have lasted a few hours. An instance of erosion to bedrock. Now, this doesn't happen very often. Bedrock is always there. The question is how deep it is. And in alluvial rivers, small alluvial rivers like this one, or streams, it's really a stream. Usually the bedrock is in feet, maybe 10 feet, 15 feet, meters, 3 meters, or something like that. As is shown in here. You can see in here, if you measure from here, this must be the bed of the old channel. And this is about, I would guess, it's about 6 feet. I believe we had a measurement out there done in the when we did the video. But the point is that this is shale. It's rock. And obviously it wasn't there before the event. The event happened in January 7th, overnight, from January 7th to January 8th. And this whole thing happened in one night, one evening. 400,000 cubic meters of sediment were removed from the site and deposited at the mouth, downstream, right in the middle of the city of Tijuana. So they had to go in there and remove all the sediment. 400,000 cubic meters is not easy, but they had to do it. It was in the middle of the town, middle of town. I don't recall the exact depth, but I would figure there was probably 20 to 30 centimeters throughout the mouth of the river, covering several blocks in both directions. It was tremendous. January 7 to 8, 1993. Interestingly, I wasn't there. When I came back a week later, I was out of town. When I came back a week later, I was told about the event and I said, oh my God, how did I miss this? Actually, I would not have been there. That was in Tijuana. And for me to get to Tijuana, it's a project. You know, I don't go there all the time. But the point is, I would not have been there, but I realized that I had met something very important. And good enough, in 6 months, I got to learn all the details of it. And we'll get to them later on. Now we have the online calculator here. We produced an online calculator, as you know, over the years. Since the year 2005, myself and my team of students in the visual lab, my lab, which I have had for since 1999, so that would be 23 years, produced more than 300 calculators, online calculators, which is which is a lot of calculators, but we basically decided we were going to calculate just about everything. We weren't going to do it with Excel anymore because Excel has a shortcoming that is not, since it originated prior to the web, then it's not readily amenable to web situations. I don't know because I don't use Excel. Maybe by now they've done it. I have a feeling that had they done it, I would have learned by now. But Excel originated in the year 1991, and the web is dated 1993, 1994. And like PowerPoint and maybe even Word, huh? I'm not sure about what I'm saying because I really, honestly, with you guys, I don't touch those projects. I mean, those pieces of software for various reasons. It's mostly a matter of religion. I am a Unix guy, and that's not Unix, that's MS. And there is a kind of a confrontation between the two in practice. Unix handles Unix, Linux, Mac, because Mac is Unix. They handle maybe, I don't know, it used to be 5%, but they're not growing. Now they're growing to about 10%. And the rest is just, you know what it is. It's Microsoft. That's the usage. My sense is that Unix is increasing, but for it to get to 20%, it'll take 20 years. By that time, I'll be in heaven, hopefully. But it will take some time. Why? That's just slow. That's the way it is. But interestingly, I should share a story with you. Recently, I found out that there's a company in Sorrento Valley, I believe, here in town, which employs about 100 engineers. Not too big, not too small. And their charge, they've been in business for a couple of years, and their business is namely to help other companies throughout the US and the world for that matter, to convert from MS to Mac. I have to see that when it happens. I don't know if this company is going to be successful, but the fact that there are companies like that, even right now in the market, kind of reveals to all of us that the trend is going in that direction. Okay, so far so good as far as making comments about things that don't relate specifically to sedimentation. The extension to m greater than 3. I had already told you that m equals 3 is the low value for Kolbe's method. It goes from 3 to 7. Since the curve plot, the sediment transport, rather the sediment rating curve, plots as an exponential curve, m equals 3 would be high intercept and low exponent. The intercept, where you can get the intercept, because you have to describe those equations in terms of intercept and exponent. So high intercept and low exponent will give you a large sediment transport, while the other case, low intercept and high exponent, will give you the opposite. That will be small sediment transport, or not too large sediment transport. We will see graphically what I'm just saying here when we look at the Kolbe method, and I'll explain to you at that time what exactly is it that it works. But we know for a fact that m equals 3 is the floor. Theoretically, the number cannot go below m equals 3. In practice, it could go above 7, but Kolbe has shown that it will be extremely hard for it to get more than 7. Now, from 3 to 7, being an exponent, that's a lot of influence, because imagine 2 to the 3 is 8, and 2 to the 7 is, I calculated the other day, it's 16, 32, 128. So the ratio is between 8 and 128. That's a tremendous ratio. And the reason or the justification is that sediment transport does vary a whole lot. And that is why it is difficult for us to pin it down. I have extensively talked about this before. If you make a 100% error in sediment transport, it doesn't mean much, because it can be done easily. So what are we doing here? 100% error sounds like a whole lot. And the answer is, that's all we can do. We have to be humble and realistic about this. There's things that cannot be precisely calculated. Sediment transport is not like hydraulics. I told you, I said this before, and these numbers are pulled out of the air, but they're good numbers based on experience. In hydraulics, you can make a 2% error, it will be fine. Not more than 2%. In hydrology, 25, 30% will be acceptable. In sedimentation, 100%. Okay, there are not too many sediment engineers out there. Sedimentation engineers, there are very few. I don't know why. maybe there's just not enough jobs out there for people to do sedimentation. Whatever it is, it's a very specialized subject. It's a fun subject. It's a subject that I took to learn when I signed up at PhD school at Colorado State University in 1973. That's 49 years ago. And I worked with it for about 7 to 10 years. And then all of a sudden I got kind of sent to do hydrology at at San Diego State, because they were missing I guess you could say they didn't have anybody to teach hydrology. And I came up on board and the head of the department said, Ponce, can you teach hydrology? I said, sure. And I started teaching hydrology. Then I wrote a book later. So that's how my hydrology expertise came about, from practice. But my core expertise is in this subject, the sedimentation, where we have done some very nice contributions like this one that I'm discussing right now. Okay, so there's also a calculator. Here's the calculator. I'm not going to use the calculator, but it's right there. You know, you can plug in the numbers, whatever numbers. The parameter K is a little bit of a fuzzy thing. And my understanding is that there is some like a bracket of range of values. We recommend the default 0.001, which kind of is in the middle of the park, or it's a ballpark figure. Then you can water discharge, bottom slope, hydraulic radius, and particle size. And the units are up here, metric or customary. The units are written up here in the references lane. And then you can run the calculation. Let me see this metric, parameter K, leave blank to choose the default. Here, we're gonna put in here in meters, say 10 cubic meters per second, bottom slope 0.005, that's a good value. Hydraulic radius maybe 2 meters and particle size 0.1 millimeter. That's a mid-grain sand, 0.1 millimeters. Because 1 millimeter is already coarse sand. Okay, we do the calculation in here, we get 6,000 metric tons per day. 6,000 metric tons per day. Yep, that's it. That's it. That's basically it. So that's just a sample calculation. Also, I am going to kind of make you aware. No, not make you aware, because you're going to do it anyway. It's part of the homework. But I've had you do a calculation on this method, and then I've had you verify it with the calculator. So what you need to do is do the hand calculation. Why? Because you have to do the hand calculation at least once. And why not do it while you're here? And then you plug in those numbers into the calculator, and it should be the same. And if it's not the same, either you're wrong or I'm wrong. And the chances of I being wrong on this one are very, very slim, because we've used this for 10 years. Okay. And I verified it manually too. So you should do that, because it helps you. Because if you make a mistake, and that's not an easy calculation, by the way, or computation. If you make a mistake, you can immediately find out that you did make a mistake, because you have a test. And there's the summary, and then that is it. So we have the lane relation revisited with online calculation. Now we have another video on the lane relation. I'm going to show this video because it's kind of an old video, and I'm just looking at it. I was looking at it this morning, and I realized at the beginning our videos were not very good looking. So let me just try to do whatever we can do here, and we'll see. It's a 10-minute video. I'm going to cut it maybe in the middle.
In 1955, Emory W. Lane presented a relation.
This video dates back to 2011, by the way, so it's 11 years ago.
Between sediment load and hydraulic variables.
So that's the lane relation.
Largely without affecting the river hydraulics. This photo shows the effect of releasing sediment-free water from a dam. A reduction in sediment load caused a reduction in bottom slope downstream of the dam, triggering channel degradation exceeding 3 meters.
This picture or this photo made Lane, Professor Lane, famous because up to that day, 1955, I do not believe anybody had written so explicitly about what could happen when you do this in a stream. You stop the stream, build a dam, hold on to the water, and obviously hold on to the sediment. But the Lane relation was not known at the time. You see, that's why he expounded on it in his paper, explained it very carefully. And from there on, we know that this thing could happen. Well, we meaning the good practitioners, because there are other practitioners out there that don't know this, and they actually go ahead and make a mistake. And I'll tell you stories about that later on.
This photo shows the effect of a sediment retention dam in a small creek. A reduction in sediment load downstream of the dam.
There's the two dams out there, one there and one behind it, where the arrow is. They were put together in 1992 to hold on to the sediment. What they didn't realize was that if you hold on to the sediment, the water becomes hungry downstream. And that's exactly what happened. This hole that you can hear, there's a hole. This is a caving or degradation, I guess you could say. It was all produced that night.
Stream to erode to bedrock about 3 meters within a short time span. Thus, as the Lane relation predicts,
the 3 meters is an observation that we did when we were out there because we were physically out there. So we just kind of guesstimated or eyeballed the amount of degradation. It was about 3 meters now that I recall.
Decreases in sediment load downstream of a dam result in hungry water. Hungry water leads to channel degradation until a new equilibrium is reached.
And then the dimensionless Lane relation. One of the issues or characteristics of our career or our contributions over the last 50 years have been putting the hydraulics in dimensionless form. And I learned that at Colorado State when I was there. There was a professor of mine, Professor Wilheiser, who had done pioneering work in making the equations dimensionless. And so I learned there, and I was able to apply it in many instances. When you make the problem dimensionless, then it becomes only one problem to solve, not many.
The Lane relation can be expressed in dimensionless form by using suitable hydraulic and sediment transport relations. 1, the dimensionless Chesney friction formula. 2, the Colby sediment transport formula. And 3, the Strickler relation for Manning's N. The following derivations are strictly applicable to hydraulically wide channels. The dimensionless Chesney formula is:
we have derived this equation already.
The Colby sediment transport formula states the proportionality between unit width sediment discharge and mean velocity. Where rho is the mass density of the water, and K sub 1 and M are coefficient and exponent, respectively, of the power function. In general, the exponent M varies between 3 and 7. K is equal to 1 in SI units and to 1.486 in US customary units. Therefore, in which K sub 2 is equal to G over K squared. K sub 2 is equal to 9.81 in SI units and 14.568 in US customary units. The Strickler relation for Manning's N is K sub 3 is equal to 0.04169 in SI units, with D50 in meters. And therefore, the dimensionless lane relation is
Let me make a comment. I don't recall exactly when we did this because the nice paper that I presented to you last time is dated 2015, but this movie is 2011. So it must have been before 2015. All I can say is that the difference between the vector and the raster. The vector we did in 2011, and then the raster we did in 2000, I'm sorry, the raster was done in 2011, and the vector was done in 2015 in a nice way with colors and everything else. But I believe that this derivation, this mathematics, dates back to the year 2011.
unlike the original lane relation, which was a proportional.
By the way, I should remember, and I just remember this, what prompted me to do this in 2011? Well, in 2009, we had made a major breakthrough in the unit hydrograph theory, because I told a student, one of you guys, to prepare a paper on it. And of course, he did it, but he didn't complete the work because it was a difficult assignment. So nice, right after the end of the semester, and he didn't complete the work, and he gave it to me, and I said, oh gosh, I gave this gentleman too tough a project. And I said to myself, how tough could this be? Well, it is tough, I know. That was 11, 12 years ago. So I sat down in about a couple days, actually, of concentrated work. I came up with the total and complete dimensionless solution for the unit hydrograph theory, which I asked him to do, but he couldn't do it. And then after that, I kind of got the strength to pursue other dimensionless presentations. And this one was one that was there in the back burner, not having dealt with. So I decided to pick it up, and we did it in 2011.
This new lane relation is a dimensionless equation. Thus, it is properly a sediment transport function.
Those of you that are taking hydrology with us, 634, we are going to cover that unit hydrograph next middle of the semester, week 10, 11. And you will see how difficult concepts were thrown in there, put together in that that I call the dimensionless unit hydrograph.
The sediment transport function is This sediment transport function is applicable in either SI or US customary units. Having assumed n equal 3, the only other parameter to be determined experimentally is K sub 1. Lower values of K sub 1 are associated with higher values of the exponent m. Assume the following example.
So this is just an example, which, by the way, you guys are going to do. So let me just finish it here. The answer is 726 newtons per second. That's it. So that is the 2011 lane relation. So I have 1, 2, 3, 4 more papers that I wanted to cover. So papers or items. So let's move on to the next one. Sediment control in Aguaje de la Tuna, Tijuana, Mexico. This is the one that I was talking to you about, where I videoed this with my Mexican friend, engineer Alberto Castro, who, by the way, is he has quite a reputation as a hydrologist and civil engineer out there in Tijuana. By the way, this movie or this video is in Spanish because we did it because we wanted to show it to them, but it has English subtitles. So you ought to be able to follow it fine, nicely. Control of sediments in the aguaje de la tuna. These were two sediment retention. Read the part at the bottom. Sediment retention dams at the aguaje de la tuna.
Buenos días. Estamos aquí en el aguaje de la tuna.
Yeah, he is my colleague Alberto Castro from Tijuana.
Una de las microcuencas que desembocan al río Tijuana en Tijuana, Baja California, México. Estamos acompañados del ingeniero Alberto Castro García, ingeniero civil hidrólogo de la ciudad de Tijuana.
Buenos días a todos. Agradezco la invitación que me hace el equipo del doctor Ponce de la Universidad de San Diego para presentarles un poquito de lo que es la hidrología de Tijuana, especialmente de este arroyo muy conocido que se llama el aguaje de la tuna. En 1991, hubo una lluvia extraordinaria en la ciudad que provocó una inundación en esta cuenca, arrojando una importante cantidad de lodos a la desembocadura. En 1996, unas lluvias extraordinarias golpearon a la ciudad y especialmente a la cuenca aguaje de la tuna, haciendo que 400,000 metros cúbicos de lodo bajaran por su delta. Como consecuencia de este,
I believe he himself evaluated the volume, which he said on the record that it was 400,000 cubic meters, equivalent to about maybe 600,000 cubic yards, by the way.
de estos estudios se llegó a la necesidad de construir obras de protección que fueron canalizaciones y muros de retención como el que aquí tenemos. Originalmente, cuando se construye, está prácticamente al nivel donde yo me encuentro parado. Este es el nivel de desplantes del primer muro de retención. El objeto de este muro era básicamente retener sólidos. Originalmente se construye el muro de retención que va a almacenar cierta cantidad de sólidos y en la vida útil de este muro que produjo la erosión se obliga a la construcción de un primer escalón, luego viene otro ciclo de 10 años, se construye otro escalón porque ya ha sucedido el fenómeno, se ha repetido el fenómeno de hidroerosión y se vuelve a repetir de nuevo en la forma en que observamos, en donde ya el nivel de erosión llega hasta roca más consolidada, que son lutitas, como se puede observar ahí. Aquí estamos ubicados a una distancia aproximadamente de 50 metros aguas abajo de la presa de sedimentos. Como podrán ustedes ver, aquí la cantidad de degradación del lecho del arroyo ha llegado hasta la roca. Es una lutita aparentemente alterada. Aquí hay un proceso geológico antropogénico en el cual se está desarrollando o creando un cañón, un pequeño cañón en el lecho rocoso del aguaje de la tuna. Aquí podemos ver una curiosidad de la naturaleza, cómo el agua que discurre en esta zona del aguaje de la tuna sobre el lecho rocoso de lutita ha podido a través de los últimos 20 años esculpir esta área que ustedes ven aquí, viene a ser una presa natural de una forma irregular
aparentemente un vertedor o vertedero, pero con cauces intermedios.
This is interesting. Observe the shape of that spillway built by nature. And I should tell you at this point that about 20 years ago, when the environmental movement got started, it was very strong, and it's still very strong, of course. We need to pay attention to what the environment, how it is, and how to take care of it. But the point that I'm making is that at that time, the Journal of Hydrologic Engineering came about, meaning it was created in 1996. As a matter of fact, I should tell you that we were lucky that we had a paper on that first issue of the journal, January 1996. But the point I'm making is that they decided to put a spillway, which is a characteristic of hydrology. Hydrologic engineers are charged with sizing the spillway, because that's a hydrology problem. As a matter of fact, we did that in a couple of places, namely at the La Calzada Dam in northern Peru. We did that several years ago, maybe 15 years ago. But what I was going to tell you is that that spillway that they portrayed, that the journal portrayed in their cover, was not a regular spillway like the old type of spillway like Cha would let us believe in 1959, where it was nice and smooth, but it was kind of an irregular spillway. It was supposed to not to be, it's supposed to be high so that you wouldn't readily recognize that it was a spillway. So kind of, it reminded me today that if they had known a different thing, they probably would have taken this little spillway, natural spillway, and put it in their magazine.
Vertedor o vertedero, pero con cauces intermedios.
Okay, we have a couple more things in here: sediment control, hungry water. We have legacy tail and a video. And then the sediment retention basins, to be or not to be. I had decided this morning that I was gonna show one vector and one raster. I believe this one's gonna be the video, and the other one's gonna be, no, I'm sorry, this one's gonna be the raster, and the other one's gonna be the vector, kind of the complement. You know, I have vector and raster, both of them. So you can, if you do both, then you're complementing. The vector score is easy to understand, but if you wanna really understand it completely, I'm sorry, the opposite. The raster, the video, is easy to understand and to grasp because it's video. But if you wanna go understand it completely, then you gotta go back to the vector, to the paper that describes the process. So we have in here hungry water. So we're finally going to define to you what hungry water is.
Rivers transport two types of suspended sediment. One, bed material load, and two, wash load. Bed material load is the fraction of sediment load whose particles.
The issue is at this point, so that we can prepare the field for later, for the next half of the course, is can we calculate bed material load? And the answer is yes. That's exactly what Einstein set out to do in the year 1950. Can we calculate wash load? Yes and no. No, because Einstein told us that we couldn't do it. And he is correct. However, he was followed by Kolbe and his associates back in the year 1955, because Einstein developed his method in the year 1950. In the year 1955, at about the same time that our colleague Lane was doing his geomorphology development, Kolbe was working on sediment transport. And he came up with a formula, modified Einstein. No, I'm sorry, that was 55. He came up with a modified Einstein. And in there, he does calculate, no, I take that back. No, he does not calculate the wash load in 1955. I'm a bit confused here tonight. But then he did 1957 COBE, where he advanced the issue, and then his 1964 COBE, which we will extensively treat later on. And in there, he kind of circumvented the problem of us not being able to calculate wash load, and he did calculate it. Interesting, fascinating. How could he do that? Even Einstein said that you couldn't do it. Well, COBE had a lot more tools at that point. It was exactly 14 years later, and I guess he felt good enough about it, and he came up with the COBE method, which calculates wash load. Okay, let's move on in here.
Sizes are significantly represented in the channel bed. Wash load is the fraction of sediment load whose particle sizes are not significantly represented in the channel bed. Wash load is the sediment size that is fine enough to be carried out by the flow without affecting or being affected by the hydraulics. The bed material transport rate depends on the hydraulics of the flow, while the wash load concentration is independent, for the most part, of the hydraulics of the flow.
When we say for the most part, we mean it. If the load is low, less than 10,000 parts per million, it will be independent. But if the load is high, let's say more than 50,000 parts per million, it would not be independent because the wash load would be interfering with the bed load. It would be like a very heavy mix of both. And then we cannot say that the wash load is independent because the presence of the wash load is interfering with the settling of the bed load, and therefore they're kind of going together at that point. So then the question at this point is, when would you get a sediment load that is more than 50,000? 50,000 sounds like a whole lot. And the answer is yes, when you have a debris flow or high concentration flows, which you every once in a while have in mountain streams. You know, an example we have here in the San Gabriel Mountains, they have recurring debris flows every once in a while, almost every year. They have a debris flow out there. Why? Because the mountain is so steep. It's the steepest mountain in the US, by the way, regarded as that. And it's not only that, it is the one that is going up at the fastest rate, which has been calculated at about, don't quote me on this figure because, you know, I have so many figures in my head, but I think it is 1 millimeter per year, which is an extremely fast tectonism, movement of the Earth's crust moving up. That's why it's called uplift, 1 millimeter per year at the San Gabriel's. And that's causing a lot of trouble. Of course, the trouble that it causes cannot be examined from year to year. You have to examine it from 100 years to 100 years. And at that point, you'll see the difference. That's just the way it is. Geological processes are slow.
Under steady conditions, there is a sediment rating curve. That is, a unique relation between water discharge and corresponding sediment discharge.
The issue of the sediment rating curve, which is a unique relation between water discharge and corresponding sediment discharge. Is the relation unique? That's the first question we got to answer. And the answer is, under steady conditions, it should be. Do we have steady conditions? Well, Mother Nature tends to go to steady. We have said that before, and we can repeat it now. So when we don't have unsteady, we have steady. And steady is the one that is more permanent and the one that shows up more often. Every once in a while, we have a flood and that becomes unsteady, right? But if the situation were completely steady, then one would have a unique relation between water and sediment discharge.
Bed material only. A calculation of sediment transport rate.
I can't do this. Oh, because it's in the video.
All points of the rating curve.
We calculated this sediment rating curve in Santa Cruz, Bolivia, back in the year 1989. I was hired on a consulting assignment over there for, it was about 6 months, 3 months first and then 3 months later. I went over there twice. and we did heavy computing out there. We developed the rating curves that you see in here, the theoretical rating curves based on different formulas. What formulas? Well, let's take a look. We used the Toffoli formula, which is used for large rivers. We put them in here just for comparison because we had the model, so we could use it. Engelund-Hansen, Akers and White. Akers and White is considered to be the most popular sediment transport formula in practice. Engelund-Hansen also for large rivers. Colby, I shouldn't say Akers and White is the more popular. I think the difference between Akers and White and Colby is that Colby is very simple, straightforward. Akers and White is extremely complicated. So some people prefer the simple stuff and they go to Colby. Others prefer to get complicated and they go to Akers and White. I cannot vouch for Akers and White. Actually, anytime you do a calculation with any of these formulas, you get a different answer. But it's not totally different. Like in this case, we have the Colby, Meyer, no, the Meyer, Peter, and Mueller, which was a gravel formula over here, low, showing low, while the others are showing high. Look at the difference. It's about an order of magnitude. An order of magnitude is 10 times more, right? And these are formulas that are applied to the same data. That means that since these other four formulas are more or less in the same ballpark, then the Meyer-Peter is not applicable to the sand bed channel. Correct. Colby is the one that's mostly applicable to the sand bed channel. And right here, you see that Colby is over here kind of nicely going in here below the other three curves, but in here it goes in the middle. And needless to say, we use the Colby a lot and we programmed it and so on and so forth. We've used the Colby for 30 years. One of the things that impressed me about the Colby is that my professor, Daryl Simons, used to say, when everything fails, I use Colby. Why? Because Colby doesn't fail. And why it doesn't fail? Because it's a chart and you cannot go off the charts because you put the limits and you're in the chart. Well, in other formulas like Einstein's that has no charts or that has too many charts, you can get yourself into a corner and not get out of it. So that is why the Einstein method is not used in practice. Everybody talks about it, but people don't use it. Even I don't have a calculator on the famous Einstein method because I know that if I ever produce that, that would be a challenge. It wouldn't be used. Not that it matters. I would like to put a calculator anyway. I can't do it now anymore. But I am telling you that we did the modified Einstein, and we developed a calculator, and we will talk about that later, and I'll have you run a homework with it. But in here, the story of this graph is an interesting story, which I may come back to discuss it again. But while we're looking at it, let me say that we use the Colby method because, well, we said we were going to use the Colby method to find our conclusions, but we're going to compare with other equations and so forth. When people hire you to do this kind of work, and if you do one method, they don't like it. They want you to do 2, 3 methods. Why? Because they're not sedimentologists. They're not hydraulic engineers. They're hiring you. They have command on what you're going to do. And therefore they require this and that, right? This has happened to me many, many times. The people that don't know require a lot because they want to make sure that you're not making a mistake. I don't know why they hire you there, but that's the way the world works. They hire you, they hire the specialist and they require that the specialist do this and that. It's happened to me many times. At any rate, so when we did this, I had the supervisor come over here and meet with me. And he asked me, he said, what method are you using? What sediment transport formula? That's a very basic question. And I said, the Colby method, because I trusted and so on and so forth, this is the story. We're going to use the Colby method. And he said, the Colby method was developed in the United States. And I said, yeah, that was Mr. Colby in Nebraska, the Niobrara River in Nebraska, a tributary, I believe, of the Arkansas. I'm not quite sure of that, but Niobrara River is in Nebraska. And he says, well, what applicability does it have to these rivers that we have in here in Santa Cruz Basin? And I said, well, you know, quartz sand is quartz sand everywhere. It's got to apply. And he says, well, we haven't used this method. And so I said, he was kind of throwing doubts as the work I was going to do. And I said, hey, don't worry about it. When the spring comes, actually not the spring, is the summer over there. But it's an odd summer because it's on the other side of the Andes. I don't know, but the climate is changed, is different. I said, when the rainy season comes, we're going to go out there and do some measurements. And once we do the measurements, we're going to plot them on this chart. In other words, the lines over there, the 1, 2, 3, 4, 5 lines are theoretical formulas coming out of the equations. And the red dots in there are measurements. We did on the site. We did 3 measurements. It's expensive and cumbersome to do measurements because you got to wait until the flood comes. And you got to, you send a crew of people out there in the middle of the flood to do the measurement. It's not a whole lot of fun. I must confess to you, I do not recall having done these measurements. I've been around, I've been advising, but not actually doing the measurements. Usually the measurement is done by a technician, which has done this measurement for 20 years, and he knows exactly what he needs to do following the procedure, right? So we did these measurements and we got these answers. So I went back to the supervisor and I said to him, see, we proved that we were right. And he agreed. He says, oh yeah, that looks good. We just wanted to make sure that we were right. But now let's take a look in here. The point samples are the red, and they're supposed to simulate Colby, and Colby's over here, right? Colby's over there, and the reds are over here. So let's just compare the theoretical value. It's 45. No, 40, over here, it's about 44, right? No, not 44, 10 to 4,000, because this is 10,000. So it's 4,000. So that the units are out there in the ordinance. So we have in here, I'm looking at this point in here of the Colby method, the dotted line, it's 4,440. And this one over here is the actual measurement, which is 7,500. So the error is what? 50, 60%? Yep, sure, 50, 60%. And over here is from 13 to 24. So that's almost double. That's 100%. So you can see, now why does this happen? It happens because you can see both ordinate and abscissa are log cycles or log scales. The variability is tremendous. So that is the reason why you cannot pin down readily the amount of sediment transport. And we got to accept the best of practice, which is what I am telling you right now.
This sediment discharge is often referred to as the, quote, sediment transport capacity, unquote, to denote that it is the amount of sediment that the river will.
Notice the curvature of these curves. They're not a straight line. They go up and then they come down, okay? Notice also that if you want to look at the M value, okay, the M value over here is high and over here is much lower because it kind of, it went up this way. So my guess would be that over here, the M value is high, maybe 5 or 5.5, and over here is more like 3.5. So this is a typical as measured and as calculated sediment rating curve, and it shows the variation of M locally. M, the value that we were discussing when we discussed the modified lane relation.
Always carry under steady equilibrium conditions. Under unsteady conditions, the following 4 scenarios are possible, and the resulting effects are noted. 1, an increase in the amount of sediment discharge at the upstream boundary without a corresponding increase in water discharge would lead to reach aggradation. 2, a decrease in the amount of sediment discharge at the upstream boundary without a corresponding decrease in water discharge would lead to reach degradation. 3, an increase in the amount of water discharge at the upstream boundary without a corresponding increase in sediment discharge would lead to reach degradation. 4, a decrease in the amount of water discharge at the upstream boundary without a corresponding decrease in sediment discharge would lead to reach aggradation.
So what is this aggradation thing? And the answer is under stable, steady conditions of water and sediment transport, there would be no aggradation or degradation. Aggradation and degradation are happening only when there's instability of the bed due to changes in water and or sediment transport. So aggradation has to be studied with modeling. Now we have models to do that for the last 30 or 40 years. As a matter of fact, when I signed up at Colorado State in 1973, that's the first job I did. I met one day with, the first day, with Professor Mahmoud, who was going to be my direct supervisor. And he said, Ponce, we're going to do sediment routing. Now, at the time I had heard about sediment, of course, who doesn't? But routing was a new thing for me. I said, sure, we're going to do it. And we spent the next year doing just sediment routing. And we discovered a whole lot of things, by the way, numerical analysis and so forth, that we discuss in my class 632, computational hydraulics and hydrology. So aggradation and degradation are two things that require modeling. Lane, of course, studied aggradation. He studied degradation. He didn't do any modeling because at the time he was doing it, 1955, there was no modeling. Modeling of this subject came about in the 70s. As a matter of fact, we were, I would say, among the first to do modeling of sediment movement, unsteady sediment in the middle 70s.
These statements are derived from the Lane relation developed by Lane in 1955. The second case in particular merits careful consideration due to its significant practical implications. This situation usually happens downstream of a dam impoundment. The dam ponds the water and retains most of the sediment. The water subsequently released is typically almost devoid of bed material load. Therefore, it is, quote, hungry water, unquote. This water will have the tendency to pick up bed material sediment as it moves downstream. The hungry water condition is exacerbated in the case of a sediment retention basin. Holding on to the sediment behind the dam and releasing the water immediately without the sediment will produce channel and bank erosion downstream. Depending on the rate of water release, the amount of erosion will be commensurate with the quantity of sediment retained in the basin. Thus, a sediment retention basin does not appear to be an effective strategy for sediment control in natural streams.
And that's the end of our statement here. And that is a truism. If you're going to hold on to the sediment at a place and then allow, or the stream going downstream in the natural channel, it is no question about it. It is going to pick up the same amount of sediment that you dropped, that it was dropped in behind the retention basin. So the structure is not going to serve its purpose of holding onto the sediment. Is there any other solution? Well, you can figure out what solution, but do not contradict or go against the Lane relation, which is a statement of practice. Unfortunately, the Lane relation, well respected among sedimentation engineers, is now well known among civil engineers or architects for that matter. Architects practice a lot in various places. And one of the problems with this particular project, that was the design was done by architects and perhaps hydraulic engineers that were not sedimentation engineers. They did not know in 1991, when they did this project, of the existence of the Lane relation. Okay, so now we're here. The next one is going to be, it's going to be vector. Sediment retention basins, to be or not to be. And at the end, I'm going to tell you a little story from my own experience. Okay, let's read this. Is it the right size? I think it's the right size, right? Sediment problems in hydraulic engineering are difficult to solve. Oh yeah, you bet. You can actually not solve the sediment problem. All you can do is mitigate, reduce the effect, look at it one way or the other, but there's always going to be a drawback in anything that we do with sediment. This is a natural process, and that's what Mother Nature said it should be. sediment is actually, if you look at it from the right perspective, it is gold. We have plenty of stories to illustrate what I just said here. It's dirt, right? How could it be gold? Well, can you eat gold? No, you get sick. No, sediment, you can eat sediment because it goes into the plants, it goes into the fruit, what we eat, it goes into the fiber also. So sediment, why sediment? Because sediment is just an agglomeration of a whole lot of things among them, the nutrients that you need in order, no, not that you need, that the plants need in order to grow, and that you need because you need the plants in order to survive, to burn your food so that you can live, right? So a case in point, in 1992, 2 sediment retention basins were built in the Aguaje de la Tuna watershed in Tijuana, Baja California, Mexico. The intent was to catch the sediments in the event of a flood while letting the water pass through. I guess the idea was that after 1991, that they had a huge flood, people said, we don't mind the water because it comes and goes, because it goes with the gradient. If you wait long enough, the water disappears and it goes into the river. The sediment, no. Once the sediment goes into the living room, you can't get it out unless you excavate it, unless you move it mechanically. So the problem was the sediment, not the water. Why is that place prone to floods? Because it's the mouth of one of the major tributaries of the Tijuana River. And mouths always are prone to floods, particularly in this area, which is semi-arid. So every 10 years, 20 years, you're gonna have a flood. First, you're gonna have a drought, followed by a flood. If you have a drought, it follows by a flood, and you're always gonna have this type of problem. There's no way we can get out of it. So the intent was to catch the sediments in the event of a flood while letting the water pass through. The short-sighted vision was that if we can hold on to the sediments, we'll let the water pass through clear and we'll be fine. That was wrong, of course. The objective was to reduce sediment deposition in the mouth of the watershed based on the belief that sediment was more damaging than floodwaters. On January 6-7, 1993, almost 30 years ago, a severe and unusual flood tested the sediment retention basins, which proceeded to fill up the sediment in short order. I wasn't there, but I was told that the retention basins had been made or had been built to hold onto the sediment, and the sediment was held by the retention basins. Apparently, the problem had been solved. However, experience indicates otherwise. To understand what may have happened, we examine Lane's relationship, which states that sediment discharge is proportional to water discharge, and that is a truism. Sediment flow, or rather water flow that carries sediment, has a want to carry that amount of sediment, which is the equilibrium sediment. If it doesn't carry equilibrium, it'll erode, or that rather aggrade or degrade. That's a fact, okay? So we shouldn't really mess with it, but we do in practice. According to Lane, if sediment load is extracted from the flow by any means and water discharge is not reduced accordingly, the water flow becomes hungry and proceeds to entrain new sediment as it moves downstream. This explains the well-known phenomenon of degradation downstream of a dam. I have developed over the years a model. And let's assume for a minute that we like to carry a load. I don't know, this is kind of not a good model, but imagine somebody carrying a load and wanting to carry every time that he or she moves a load. So if you say to this person, you know what, you're not gonna carry this load anymore, maybe you carry half of it. And he or she is gonna feel light. I mean, I'm not carrying my regular load. Okay, so that's the argument with people. But in terms of nature out there, the sediment does not think about that. The sediment is going to want to pick up the load that it carries. That's a law established by Einstein in 1950. And we will have a chance to read in much detail the paper by Einstein that says all these things. This explains the well phenomenon of degradation downstream of a dam, which of course Lane expounded on for many, many times and finally wrote this paper. In the event of January 1993, approximately 400 cubic meters of sediment were deposited near the mouth of the Aguaje de la Tuna, despite the fact that the sediment had retained all the sediment they could which was 20,000. So see what happened. The sediment were designed to retain 20,000 because that's all they could. That's all it could fit into the low dams that they had built. They figured 20,000, they didn't do the calculation, so they did it for 20,000. About 420,000, two scenarios are possible. This is what I am speculating in here. Two scenarios are possible. About 420,000 cubic meters of sediment measured as sediment deposits at the mouth. There's a typo in there, I got to fix. Came down the watershed that night. 20 were retained by the basins, and the difference, 400,000 was transported to the mouth. That's one way of looking at it, because 400,000 were transported to the mouth. That has been measured. 20,000 were retained in the dams. I mean, yeah, in the two dams. So that has been measured too, by the way. The volume is easily measured. So the first conclusion would be, which is wrong, by the way, that 420,000 came up, 20 were retained, and 400,000 showed up at the end. Second scenario, about 400 cubic meters came down, 400,000 cubic meters came down. 20,000 were retained by the basins. An additional 20,000 were later entrained by the hungry water, and the sum, 400,000, was transported to the mouth. We believe that the second scenario, according to the lane principle, is entirely possible and overwhelms in terms of the lane relation the first scenario. First scenario would be somebody that doesn't know that the lane relationship exists. The second scenario is now that we know that there is such a thing as sediment transport, and the water is going to pick up the sediment if you don't give it to it, or if you take it away from it, it will pick up. According to Lane's relation, the second scenario appears more plausible. In the Aguaje de la Tuna, Aguaje, by the way, is a Spanish word that means small river. A small river with a little bit of water. The hungry water outflowing from the sediment retention basin scoured a depth of about 3 meters in the stream bed down to bedrock. See photo. We have another photo in here. I took several photos. Right there. It's a classical photo. Down cutting to bedrock at Aguaje de la Tuna, Tijuana, Baja California, Mexico. Notice one of the sediment retention basins in the background. There it is, the sediment retention basins, which, by the way, they're still there. Okay. Thus, the utility of building a sediment retention basin without providing for concurrent water storage is open to the question, meaning you can't just try to hold on to the sediment by building a sediment retention basin. What are we saying in here? Does it mean that these sediment retention basins cannot or should not be built around the world? And the answer is yes. If you're following everything I said in here, you should not. However, if you want to protect the downstream stream so that it doesn't erode, then you can do it. That's a lot of work, and there's a lot of cost involved in doing this, but it can be done. Otherwise, the sediment retention basins in a situation like similar to the one that we just narrated would be a waste of money. So that's why this story is called To Be or Not to Be. So that's, now I am going to, in here, I'm not going to show the video because the video says basically exactly the same. But I am going to say that in the year 2000 and when was it? The year 2009, or was it at 8? I believe it was about the same time that we did this in 2008. I had a meeting in northern Peru with the design team because the boss, who was a civil engineer who got the contract to do the study, had hired 7 people, 7 engineers in various parts. He hired them in California. I believe one of them came from Oregon. Another gentleman from Spain. He was going to be the dam designer because this was design of a dam, and a dam have the appurtenances. Has a lot of things. It was a team of 7 people that were designers of this dam. 2008, 2009. And the designer of the dam, who was a geotechnical engineering, he designed earthen dams, which is a specialty in itself, had recommended to the boss the person in charge of the entire project, that there was a problem with the issue of sediment. That even though we were going to design 2 dams that were going to manage the sediment that could accumulate in these 2 dams, we wanted to design an in-stream dam and an off-stream dam. The off-stream dam for the purpose of managing the sediment that surely was going to collect in the in-stream dam. And that has been done in other places. And as a matter of fact, engineers for the last 30 years have been not recommending or not encouraging in-stream dams because they fill up with sediment. There was a case up in Hemet, in the Hemet Valley, up here north of here, maybe 2-3 hours from here, where they had that problem. They had to build this dam. I don't remember the name right now. They keep changing the name. It's a huge dam out there next to Hemet. Hemet is here in California. And they had 4 sites. And there was one site that was off-stream. And that's the one they chose, even though it was costlier. It was more money, but they figured we don't want to handle the sediment. So they stayed away from the in-stream dam. Likewise in here, we were going to have an in-stream dam because of the flood control benefits and so forth. But we wanted to put 2 dams so that we could manage it, kick it around and so forth. And this has happened, by the way. There's a dam in Peru, or reservoir rather in Peru, which doesn't have a whole lot of sediment. It's 50 years old and it's 10% or 8% or 9%. Last time it was measured, it was 8% or 9%. That's excellent, because that means in 50 years it filled 10%. If you extrapolate, it will take 500 years for it to fill up, or 450, which is a heck of a lot. That's very good. That is very good. We don't design dams for more than 100 years because we figured 4 generations and that's it. But this particular dam has very little sediment accumulated behind the dam because of the management. So we decided we were going to do this in the same new dam out there, which, by the way, hasn't been built yet, but it will be built eventually. But then the meeting was because the geotech gentleman coming out of Spain had recommended that he was concerned about the amount of sediment coming up from the hill. This is the Andes, and it goes all the way to, in meters, 4,500 meters, which is 15,000, 16,000 feet elevation of the peaks. So it is to be expected there's going to be a lot of sediment. And in fact, as a matter of fact, throughout the coast of Peru, there's a lot of sediment movement because the mountains are very high and therefore there's a lot of gravity and it rains quite a bit and so on and so forth. The result of that, fisheries off the coast of Peru is some of the richest in the world. Fisheries? Richest? What are we talking about here? Well, if there's a whole lot of sediment and the sediment is coming down, it'll go into the ocean. And once it's in the ocean, it will form part of the base of the food chains that will develop. So that is why, like I said, fisheries off the coast of Peru is extremely rich, and it has always been extremely rich. So therefore, that's the reason why there's a lot of sediment off the coast on this side of the mountains. So the gentleman wanted to see if we could retain the sediment before it gets to the main dams upstream. And he was recommending as an idea to build a few or find some sites out there where you could build these small dams that could hold onto the sediment. And so the boss called everybody, the entire project. Actually, it was not the entire project. It was the designer, myself, because I was the hydrologist of record. There was another gentleman who did the geology, and the boss. We met over in northern Peru in Chiclayo one night to discuss the issue, if this was a good idea or not. So then the boss said, I remember that very clearly. It was sometime in January or February of 2009, I believe. He said, so-and-so has recommended that we put these small sediment retention basins. Ponce, what do you think? And I said, no, that's no good. According to the land regulation, and of course, I did not expect them to understand what I was saying, but I was talking about it. That is counterproductive, it's a waste of money, and so forth, because I spoke about it. So it seemed like I had some sense. So the boss was, since he's just a straight civil engineer, bridge designer, he didn't know. Okay, so at that point, it was my opinion against the opinion of the other gentleman. So he did something really smart. He called upon the opinion of the third gentleman, who was a geologist who had practiced geological engineering, which is kind of very much related to soils and geotech, right? He was an older gentleman. at least 10 years older than than I was at the time. So at the time I was maybe 60, 62, 63, and he was 70, 75. And then he gave an opinion. I remember very clearly when he said, well, we know for a fact that dirty water does not erode and clean water does erode. So I side with Professor Ponce. He basically said what Einstein had said in 1950. So that was the end of the discussion. Okay, so I'm giving you that example from my own practice to show that these issues continue to be discussed all over the world. What should we do with the sediment? We don't like it. Although, you know, some people like it, some people don't like it. There's other stories that I will tell later on. I don't have the time now. Thank you very much. See you Thursday at the same time. Bye-bye.
Thank you, Professor.
Okay, you're welcome. Bye-bye.